Okay, hello class. What I'm going to try to do right now, real quick, during seventh period, is I'm going to lecture to an empty classroom about impacts and extinction events. So if you are watching this video and I was not in class today because I had to have a little last minute absence uh, so I could go to a sonogram with my wife. So the hospital just changed their policy, and I am now allowed into the room when the sonogram is happening, and I would like to see that. So if you're watching this video in first or second period, that's what I'm doing. So I'm going to go ahead and record the video today so we don't have to lecture tomorrow in class. So this is impacts and extinctions, and we're going to talk about obviously asteroid impacts and meteor impacts and extinctions that have come from those, and I assume some extinctions that have come from non-impacts, but we will see. So we go through the objectives. They start off with the Chelyabinsk meteor from February 2013. Y'all are probably a little young to remember this. This is what, 8 years ago now, and so that's going to make y'all pretty young when this happened. So right now, do me a favor, pause this video and do a YouTube search for Chelyabinsk meteor. You can just type in Chelyabinsk, and you're probably going to get a lot of videos about this meteor. So what this was a small asteroid traveling about 20 times faster than a speeding bullet, entered Earth's atmosphere and exploded. The good news is it exploded in the atmosphere. It got too hot, some gases expanded, and it blew up in the atmosphere and burned up in the atmosphere. It did not hit the ground, and that is a key part for probably why you don't know this meteor. If it had hit the ground, it would have been a lot worse, but it didn't. So people living in the Russian town of Chelyabinsk could feel the intense heat from the fireball as well as the shockwave from the explosion. This was crazy. It was a huge explosion. I don't know. They will probably go over it. No. They go over on the next slide. So we will see exactly how big this explosion was. Like I said, the meteor did not hit the Earth. It exploded in the atmosphere and actually the stratosphere about 15 miles above the Earth's surface, releasing the energy equivalent to 20 to 30 World War II era nuclear weapons. So you imagine the atomic bombs that were dropped on Japan, and you're talking 20 to 30 times that amount of energy. Largest known asteroid to enter the Earth's atmosphere since the Tunguska airburst, which was another kind of mysterious event that happened over Russia that we actually had a hard time figuring out. So here is the Chelyabinsk event. Here is the Tunguska event. Here is Moscow for reference, closer to Europe. The Chelyabinsk and the Tunguska event were kind of central Russia. I guess Chelyabinsk isn't super central, but there's a map for your geographical pleasure. And then before entry and explosion, no one knew it was coming. Meteor astrophysicists were looking in the other way, tracking a much larger and completely unrelated asteroid. And so literally, we were looking the other way. A bigger asteroid was coming. It wasn't coming that close to Earth, but it was big enough that we were all looking at it with our satellites and our telescopes, and literally nobody saw this Chelyabinsk meteor coming from the other way. And so when it exploded in the atmosphere, it damaged more than 7,000 buildings in 6 different cities. Most of this is windows. Blew out lots and lots and lots of windows. Many of the injuries, about 1,500 people required medical attention. The vast majority of those are going to be cuts from glass and damage to hearing because of the blast itself. People were confused and frightened about what was happening. Mobile phone networks were overloaded with calls. Office buildings evacuated and schools closed. Broken windows in homes required immediate attention due to weather. You live in Russia, so it's probably going to get cold. And so, yes, that was a big event. There's lots and lots of videotape from it. Lots of dash cam cameras, so you can see the actual meteor coming into the sky and then blowing up. Origins. So 14.1, Earth's place in space. They're going to go back. We're going to take a big picture look. We're going to look at the origin of the universe with a Big Bang. how the first stars started to form about 13 billion years ago. So roughly over a billion years after the Big Bang is when we first got our first stars. How the first star cycles started to happen. We get our first supernovas and death of stars. And it's not until you start to have your first supernovas that you can actually get your first planets. When this first group of stars formed about 13 billion years ago, there were no planets at that time. Or if there were planets, they were the youngest, very first planets. So this is a convoluted little map here. It's like a time map in a spiral. So the most recent era is the Cenozoic. This is what we're doing right now today. And then you go down the spiral, back in time, back in time, back in time, all the way back to the origin of the solar system, and then the Big Bang, which happened before that. So kind of a nice image accompanying all of history as we know it, all the way back to the Big Bang. 5 billion years ago, a supernova explosion triggered the formation of our sun and our solar system. So as the sun formed, the accretionary disk rotating around the sun ended up becoming planets. And those planets are the planets that we know today. So they talk about the solar nebula. They show our solar system and the planets involved. I believe that these are accurate as far as size, but obviously not distance. You have all your planets roughly relative to size, but not to distance. Asteroids, meteors, and comets. So they talk about asteroids. They talk about meteors. Remember the three different phases of meteors. Meteoroids are in space. Meteors are the shooting stars that we see burning up in the atmosphere. And then a meteorite is a piece of a meteor that has made it all the way down to the surface and is now on Earth's surface. They mentioned comets and the tails on comets. Let's see. They go through details of each of these asteroids, comets, meteoroid, meteor, meteorite. And they show you the relative location of both the asteroid belt, which is in between Mars and Earth, and the Kuiper belt, which has a lot of comet material and other type of asteroid material past Pluto, really. Actually, it's kind of where Pluto is. So past Neptune and Uranus, out where Pluto is hanging around in the Kuiper belt. Here's the Hale-Bopp comet. Is that an actual picture? If that's an actual picture, that's a pretty good picture with the mountains in the foreground, the comet in the background, the nice tail and everything. That's actually pretty nice. I wouldn't have any reason to believe that this is not a real picture other than how nice it is. Just seeing something that nice of a picture, my immediate reaction is fake. But I don't know, that could be a real picture. So 4.2, airbursts and impact. So this is kind of detailing what happened to the Chelyabinsk meteor is an airburst. So objects enter the Earth's atmosphere at anywhere in between 12 to 72 kilometers per second. That's 7 to 45 miles per second. So imagine going 45 miles per hour. They're talking about going 45 miles per second. These are going to be going very, very fast. Most asteroids are going to be metallic or stony. They're going to be made of some sort of rock or some sort of metal. And as they come into the atmosphere, the friction of the air itself is going to heat them up, and they're going to get very hot. If they get hot enough, they can explode into an airburst. So the object explodes in the atmosphere anywhere from 12 to 50 kilometers above the surface. Their example is going to be Tunguska or the Chelyabinsk meteor. Or they cannot explode, and in that case, they will actually hit the Earth. They will collide with the Earth as a meteorite. If it's a small one, like a meteorite, that's maybe not going to be a very big impact. If you have a large asteroid or a larger object, that can be a much bigger explosion or impact event than just a tiny little meteorite hitting, obviously. So let's look at our different layers of the atmosphere. So they're showing the meteoroid. So out in space, before it gets into the atmosphere, it is still considered a meteoroid. Once it hits the atmosphere and starts to heat up and burn up, we call it a meteor or a shooting star. Shooting star is not a scientific term; it's just a colloquial term. Meteor is going to be your scientific term. So we call it a meteor. Uh, if it burns up in the atmosphere or it explodes in the atmosphere, explosions are going to be called airbursts. But either way, burning up or exploding, they're not going to hit the surface. They're going to burn up and completely disintegrate somewhere in the atmosphere here. If they don't explode into an airburst or burn up, they will hit the ground as a meteorite. If it's just a tiny piece of rock, you may not have a big impact. You may not have a crater. It could just be a rock falling from the sky. If it's big enough and moving fast enough, it will hit the ground with enough energy. It will create some sort of crater. You might even see a flash of light from it hitting the ground, and you will have a crater left over afterwards. So they talk about impact craters. When we find these after the fact, they provide evidence that meteor impacts do happen. Their example is the Barringer crater in Arizona. I may have showed you a couple pictures of this crater in Arizona. Let's take a look real quick, because this is actually a nice little area. If you ever go on a trip to Arizona, you can stop and check out this crater. Meteor Crater, Arizona. Go to images, and yeah, you see the nice big crater here. Let's view this image. Oh, so edit image. Let's see. Yeah, here's another one. Let's view this image. There we go. So this just shows the big crater. At the bottom of the picture, you see the visitor center where you can go and visit. And then I believe, I don't know if you could climb down into the crater, but I imagine you can. There's a road that goes around the edge of the crater. This one in Arizona is one of the youngest craters that we have discovered on Earth. This one is relatively young and provides us with a lot of information about what's going on. So let's go back here, now that you've seen a picture of the Barringer crater in Arizona. Let's see. Features of impact craters are unique from other craters. They've involved high velocity, energy, pressure, and temperature. Kinetic energy of the impact produces a shock wave into the earth, which compresses, heats, melts, and excavates material. Rocks become metamorphic or melt within other materials. And so this is just a good description of how violent these impacts are and how much energy is released here. Here's a map of extraterrestrial impact craters. So everywhere you see a dot is a crater from some sort of alien meteoroid coming and hitting Earth. So here in Texas, we've got a couple down near your El Paso area. Not at the I don't know what you would call this. It's not the Panhandle. It's like the opposite of the Panhandle. But in southwest Texas, you've got a couple impact craters. And then we have one over here in the east. And honestly, I've never visited any of the impact craters in Texas. Maybe I should. That seems like a pretty interesting thing to do. Also have one up here in Oklahoma, one up here in Kansas, and those are going to be the closest ones to us. But you see, we got a pretty good spread of impact craters around here. And to be honest, this looks like a pretty random distribution. If you just imagine rocks falling from the sky, there wouldn't be really any reason that more rocks would fall in one area than the other. And so this kind of makes sense that we kind of have them spread out all over the map here. Probably a little bit harder to find them up in the mountains, in the Rocky Mountains. Also probably a little bit harder for an impact crater to form in the mountains. So that might be why you're not really seeing a lot over here in the mountains. Not that they don't happen, just that they're harder to find. So impact craters can be grouped into two types: simple craters or complex craters. Simple craters are typically small. Your complex craters are very large, usually greater than 4 miles in diameter. The rim can collapse more completely. The center uplifts following an impact crater. There's just more stuff going on than your general small craters that we find. Ancient impact craters are difficult to identify because of weathering and erosion. Weathering and erosion will usually fill them up with sediments, and it just makes them very difficult to discover which is one of the reasons it took us so long to discover the crater for the dinosaur impact, the dinosaur killing impact down in the Yucatan Peninsula, was that crater is completely filled up. It's not really a crater anymore. And so it took us quite a while to be able to figure out exactly where that hit and how that formed. So here's a good example and another picture of the crater in Arizona. They have a couple things labeled in this picture and a nice side cut diagram to kind of show you what the crater actually looks like and what you have down in the bottom and what you would expect to get to if you tried to dig down into this crater. Here's the Chesapeake impact crater. This is off of the eastern seaboard here, kind of right on the shoreline. And they show you how complex this is. Compared to the small crater, which is pretty much a giant hole that's just been filled in. The layers look normal. Everything looks normal if I were to just dig a hole into the ground. That's kind of what it would look like. But if we go to the bigger impact crater, there's a lot more going on. You don't have that whole kind of image of the sediment being removed from the ground. You have several different layers that have moved up and down. It's just very difficult to see and identify this impact crater the older it is and the bigger it is. Also, you can see the layers have kind of filled in over top. And so what used to be my big crater down here has all kind of filled itself in. And so these things are very difficult to kind of spot as you're looking from the normal human perspective, which is right at the ground. So this is a complex impact crater in Quebec, and you can see how filled in this is. The center of the crater is completely filled in, and the rim is actually like the circular lake now. And so even with a good map, if you weren't really getting the aerial view of this crater, you may not notice just how circular it actually is, especially with this kind of little inlet bay over here. But from above, you can really see the circularness of this lake. And there's not a lot of explanations for how a round lake would form like this. Rivers don't generally run in circles. There's not a lot of ways that this could be formed without some sort of giant meteor impact. So they got a list of notable impacts here, all the way from way back, the birth of the moon and the Earth and the Mars-sized body that hit the Earth to create the moon, all the way up to the most recent one, the Chelyabinsk airburst in Russia in 2013. So you can kind of scan the list and see if there's anything major that interests you. But here's the Barringer crater from Arizona that we looked at earlier. About 49,000 years ago was when that happened. So one of the most recent impacts on the Earth. Let's see. Craters on the moon, impact craters on the moon. Most impact sites on Earth are in the ocean where they are buried or destroyed. We do have a lot of water. The majority of the Earth's surface is water. So impact craters on land are now generally subtle features because they've been eroded or buried by debris. Smaller meteors and comets tend to burn up and disintegrate in the Earth's atmosphere. So we don't even have like tiny impact craters because the tiny things never make it to the surface. They burn up. Uniformitarianism, gradualism, and catastrophism. So catastrophism was where we started. Basically, the idea was the Earth was really young, and in order for all these crazy things to happen, like mountain ranges and the Grand Canyon, and all the different things we see on the surface, they had to have happened very quickly in a catastrophic event. Gradualism or uniformitarianism is what we operate under today. This is the idea that the Earth is very old. The changes that have happened in the Earth have happened over very long periods of time, and those changes are still happening today. The things that we can see happening today also happened in the past. That's uniformitarianism. So we still use uniformitarianism today. We may have spruced it up and made it a little bit of a better theory, but in general, this is the operating theory for today. Let's see. It does say it led to a new concept, punctuated uniformitarianism. And basically, this is the idea that some things in geology don't happen steadily. For instance, volcanic eruptions. Yes, volcanoes have always happened on the Earth, they don't happen every single day. And so there might be a moment in Earth where you have much more volcanic activity and therefore much more catastrophic type events than you would in a normal year. And so that leads us to this punctuated uniformitarianism. Uniformitarianism is correct. It's more the gradualness of it. It does change gradually over very long periods of time, but there are immense moments and times where everything changes. So a good example of that would be the extinction event caused by the impact of the dinosaur-killing asteroid. That would be a moment that is catastrophic and actually changed most of the environments on the Earth. And so it's a little bit of a compromise between catastrophism and uniformitarianism. So 14.3 max extinctions, sudden losses of large numbers of plants and animals relative to number of new species being added. Usually this is going to define the boundaries of our geologic time periods. So, the end of the Cretaceous is going to be a mass extinction event. Many of the large sections of the geologic time scale are punctuated by when a whole bunch of species died off. That's a really good way, as we look back into the rock record, to know when our major changes on Earth were. When something happened that kills off a huge number of the species on Earth, that is, by definition, a Earth-changing event. So usually to involve rapid climate change triggered by plate tectonics, volcanic activity, or extraterrestrial impact or airburst. And I will say plate tectonics and volcanic activity go hand in hand. If your plate tectonics increases, your volcanic activity is also going to increase. So the 6 major mass extinctions throughout history, we're going to go start old and go young. So the Ordovician is going to be the oldest one, 446 million years ago. Continental glaciation in the southern hemisphere. We had a lot of species die off, and they're saying it's because of a ice house where most of your southern hemisphere is going to have glaciers on it. Permian, 250 million years ago, volcanoes causing global warming and cooling caused a huge amount of the species to die off. Then you have your KT boundary, your Triassic-Jurassic boundary. Is that the KT? No, the KT is a Cretaceous Paleogenic boundary. Pretty sure. So Jurassic-Triassic boundary, 202 million years ago, volcanic activity associated with the breakup of Pangaea. And then your Cretaceous Paleogene boundary, KPG boundary, which is 65 million years ago. This was the dinosaur asteroid. So asteroid impact that kills off all the dinosaurs. And then your Eocene period, 34 million years ago, plate tectonics is what caused that big die-off. And then your Paleocene epoch, initiated by an airburst, continues today, caused by human activity. And so these are your 6 major mass extinctions of Earth's history, essentially. Let's see. Mass extinction events, they have them all listed out here. What is this? Number of genera, and I assume going extinct. So they're showing in the Cambrian, we're doing good. We're getting more and more genera. Oh, so I guess this is total number. Is this going extinct or is this just total number? I guess this is total number. So Cambrian, Ordovician, climbing. End of the Ordovician or late Ordovician, we have this die-off. So this is your first mass extinction event as that number comes down. Then obviously when everything dies off, we have a lot more free areas for new species to occupy. So we have a big boom. Oh, my power died. We have a big boom and all of your species kind of they don't come back. New species fill those voids. We grow. And then we have our late Devonian die-off. So we come all the way from over 1,000 different genera and come all the way down to less than 1,000. So there's your late Devonian die-off. We increase species again, and then we do some back and forth as we kind of stay level. And then into the Permian, we die off. And look at so many species died off there at the end of the Permian. We came down to a very, very low number of species. Let's see. I'll have to put this in. I don't know what happened. I don't know what's happening, yo. This is bad video production. So anyways, we got our late Devonian, we have our late Permian, we have our late Triassic, and then our late Eocene die-offs here. So the KPG boundary mass extinctions, if we go back, this is the one between the... Oh, can I go back? Previous. Yeah, this is going to be the one between the Cretaceous and the Cenozoic, I think. Previous year. Let me see if I can plug this in. That would actually help. Okay. Okay, sorry, had to go plug my laser pointer in. So yes, they're calling the KPG boundary between the Cretaceous and the Paleogene, and so I believe this is going to be your KT boundary right here, but we'll see. So talking about the KPG boundary, 70% of all genera died and set the stage for the evolution of mammals. So first question they're asking, what does geologic history tell us about the KPG boundary? We've got a couple little bullet points here. Walter and Luis Alvarez decided to measure concentration of iridium in clay at the KPG boundary in Italy. Fossils found below the layer were not found above. How long did it take for the to form the clay layer? Iridium deposits say that the layer formed quickly, probably extinction caused by a single asteroid impact. So what they're noticing here is they're finding fossils below that layer that were not found above. That tells them that those animals were living before this layer was put down, but not after. And how do you form a layer so quickly as so many animals are dying off? It only makes sense that it's some sort of asteroid impact is going to throw up a lot of ash, a lot of dust, a lot of material into the atmosphere, and that dust is going to settle all over the world. And so even, I don't know exactly, they're looking in Italy. So even over in Italy, because the asteroid hit in Central America, even over in Italy, they're still getting this layer of dust and dirt and debris from the actual asteroid impact. So Alvarez did not have a crater to prove his theory. Like I said, it took us a long time to find that crater, but eventually we did. It was identified in 1991 in the Yucatan Peninsula. It's roughly 112 miles in diameter, nearly circular. It's about half on land, half out in the ocean. And then we have a lot of kind of surface features that we can still see that lead us to believe that it is there. And then also, if you look through seismic data explored there, you can see features of that actual crater. And so this is where the dinosaur killing asteroid actually hit, right almost centered in between land and sea, and not too far away from Texas. It's down here in Mexico, right off the Yucatan Peninsula. So let's see. Sequence of events. They have the asteroid coming in. The asteroid impacts Earth and sends out the shock wave. And then seconds after the impact has actually happened, you get your ejecta blanket. So this is all the material that was thrown up into the air, starts to settle down onto the surface. You get your mushroom cloud from your huge explosion and impact. Fireball sets off fires. Sulfuric acid enters the atmosphere. Dust blocks out sunlight. Tsunamis from the impact reach over 300 meters or 1,000 feet high. So now we looked at how close Texas was to that actual eruption there. If we go back just another slide. So imagine this part of Texas getting like 1,000-foot wave coming up onto shore and just wiping out anything that's there. This was a definitely world-changing impact. So months later, after that impact, after the tsunami and the ejecta go everywhere, you still have no sunlight, no photosynthesis going on, acid rain falling. The food chain has essentially stopped. Without sunlight, without photosynthesis, from the smallest to the largest animals are having trouble eating and surviving. Several months later, your sunlight is slowly starting to return. Your acid rain is trailing off. Ferns restored on burned landscape. So we're starting to see the most robust plants come back after everything has kind of been burned away and died off. So you're starting to see the comeback of Earth. Impact caused mass extinctions but allowed for evolution of mammals. Another impact of this size would mean another mass extinction, probably for humans and other large mammals. However, impacts of this size are very rare. They occur once every 40 to 100 million years. To be fair, how long ago did this one happen? 65 million years ago. So we're right in the range for it to happen again. Smaller impacts are more probable and have their own dangers. I will point out, when you talk about probabilities, us being in this range doesn't make it any more likely or any less likely to happen. It's still just a set number of chances that this can occur. So 14.4, linkages with other natural hazards. Obviously, that impact is going to set off just about everything. We talked about tsunamis, wildfires. Obviously, there's going to be earthquakes from the impact itself. Mass wasting, lots and lots of landslides. With all of that shaking and earthquakes, if there are any landslides ready to go, they're going to happen. With your acid rain and blocked out sunlight, that's also going to contribute to more landslides as plants die off and acid rain starts to eat away at different things and contribute to erosion and weathering. Climate change is going to change how our storm systems, how our air and water flows, and then volcanic eruptions are also going to play a part in the aftermath of this impact event. So minimizing the impact hazard, risk related to impacts, there's really not a lot we can do. Large events have consequences that will be catastrophic. Smaller events are regional catastrophes. There's really just not a way that you can, on an individual level, prepare for this. The kind of preparation that you're looking for to actually reduce the effects of these kind of events, as they're implying up here, minimizing the impact hazard, risk related to impacts, is going to be like countrywide, statewide, having evacuation plans, having robust aid systems like I hate to use the Salvation Army, but something along those lines to actually deliver help in a fast and efficient way. So risk from impacts is relatively high. What? Relatively high? Probably that you will be killed. That's low. I don't know. I don't know what they're arguing here. They're saying that you're more likely to be killed from an impact of an asteroid than you are from drowning or from a car accident. And I just don't think that's true. I think they're doing a little bit of extra math in here. Probably didn't need to be done. However, that is average probability over thousands of years, which makes no sense because humans don't live for thousands of years. We live for less than 100 years. Events and deaths are very rare. And to be honest, nationwide or like worldwide over thousands of years, how many humans have been killed by impact events? Give me that solid number and let's talk about that. Identifying nearby threatening objects, we obviously want to look out into space and try to see what's happening. We're doing that with near-Earth asteroid near-Earth asteroid tracking using telescopes and other space-faring vehicles to try to keep an eye out for asteroids. Like this one, asteroid 234 Ida. This is one that we spotted. It's roughly, if you look at this, I'm looking at maybe 40, maybe a little bit over 40 kilometers long, maybe close to 50. So pretty big asteroid here. It's got its own set of craters on it, and so not a small rock by any means. So options, once a hazard is detected, we have none of these options except for evacuation. These are futuristic. Blowing it up in space could be an option. Nudging it out of the Earth's orbit could be an option. When you get into the math of these, they really only exist in science fiction. Blowing up an object is going to give you smaller pieces, which is going to be actually harder to handle and can have their own problems, like radioactively raining down on Earth. Nudging it out of Earth's orbit for something even like a tiny asteroid, like we saw on the last page, that's only maybe 40 or 50 kilometers. You're talking an immense amount of energy. Our ability right now today with the spacecraft we have to move something like this is absolutely zero. So 1 and 2 are not realistic options. Maybe fast forward 100 years in the future, sure, maybe we could take care of that, possibly if the situation were perfect. But really, evacuation is your only possibility. For that, you're going to have to find out about this early. The area you would have to evacuate, we're talking states, entire states full of people, possibly entire countries for a large impact. The realistic chances that you actually evacuate properly before a large impact are going to be pretty small. So let's see, the Torino impact hazard scale, they go all the way from no hazard all the way to 10, 10 being a collision will occur with object capable of global climatic catastrophe that threatens civilization once every 100,000 years or more. So this is like the big one. So this is like the dinosaur ending asteroid being a number 10 on this scale. So let's see, largest known asteroid to have entered the Earth's atmosphere since the Tunguska event. So we circle back around to the Chelyabinsk meteor. So largest known asteroid to have entered the Earth's atmosphere since the Tunguska event. Both Tunguska and Chelyabinsk were airburst events, so they did not hit the Earth's surface. They blew up in the atmosphere. The Chelyabinsk meteor turned into a fireball, and blast was video recorded by numerous people and sensors monitored by the U.S. government. These recorded, like I said, are going to be people in dash cams and different security videos all around Chelyabinsk, Russia. And so there are quite a few videos of this meteor coming in. Many of them, it just looks like people just keep driving, like they may not even seen it. But you see the meteor come in, blow up. It basically goes from roughly nighttime to daytime in just a matter of a second, and then the light's gone and you're back to nighttime again. So explosion of the meteor compressed the atmosphere. Gases generated massive amounts of heat. The meteor erupted into a fireball, then exploded and produced a tremendous shock wave. Here's a picture of someone cleaning up glass outside of their building. And so most of the glass in a lot of the buildings around these areas were broken out, like almost every single window. Many of the injuries were from glass, from flying glass, or possibly hearing damage because of the blast itself. So let's see, applying the 5 fundamental concepts. Small meteorites collected from a hole found penetrating a frozen lake. So they did find parts of this meteor afterwards. They had to go out on a frozen lake, and they had gone through the ice into the frozen lake. Long meteorite fragment found at the bottom of a lake 8 months later. Composition and density of the meteor was determined. Chondritic in composition. Density about 3.6 grams per meter, or grams per centimeter, so 3.6 times that of water. Total weight estimated to be about 11,000 tons, 11,000 tons of weight. And I believe this is going to be very metallic. This is a more metallic meteor. Location of explosion was important. Catastrophic damage if closer to the ground. If over an urban area, millions of deaths could occur. Because this happened in like remote Russia, it was just about as good as it could have been. I don't believe that anybody died. I think it was mostly just injuries due to glass. And so here's a picture of the meteor that they found. Here they are getting that actual piece of meteor. I don't know that this hole is a natural hole. They could have opened that up to actually try to get the meteor out themselves. And then how could the effects of an impact be minimized? Obviously, like I said, there's nothing we can do beforehand other than evacuate. So your evacuation hinges greatly on your ability to predict when and where the meteorite's gonna hit. So we got to see it coming. We have to see it coming with enough time to do computer models and calculate exactly where it's going to hit. And then we need to warn those people and actually have a place for those people to go. So smaller extraterrestrial objects like the Chelyabinsk meteor are not easy to spot. They're not easy to figure out where they're going. Scientists were tracking an unrelated larger meteor at the time of the Chelyabinsk meteor. Funds appropriated to identify 90% of the objects 150 meters or larger are insufficient. So what they're saying here, we look for this stuff, but the stuff we look for is only the big stuff, and we're not going to see all of it. You just can't look in every single direction all the time. Technology is available, and as it improves, it could identify even smaller near-Earth objects. But until that technology comes about, it's going to be pretty tough. So they're giving you kind of size comparisons. Here was the asteroid that we're looking at. So relatively bigger than the Chelyabinsk one. It's coming by Earth. It comes close, but not that close, in between us and the moon. And then, is that in between us and the moon? I assume it is. That looks like a picture of the moon, but the moon doesn't have a separate orbit, so I'm not really 100% sure. But you can see how close the asteroid comes, and that we were literally looking the other direction. We were looking this direction. The Chelyabinsk meteor came in from the backside and hit on Russia. And so you can see it was much smaller. It was only 18 meters roughly. So we aren't even looking really unless we see them. We're not even looking for objects this small. This is smaller than the space shuttle, but it caused a huge explosion because of the speed that it came in at, coming in very, very fast into the atmosphere. So that is it. That's the chapter 14 summary here. Obviously, the PowerPoint is posted. If I don't know what to say now. So this week, let's just remind you what we have going on this week. We just finished our last lecture over the last chapter of the book, minus chapter 13 for wildfires. We're not going to go through that one. So tomorrow, which is Wednesday, we will talk about the signature assignment, and I will do a video about the signature assignment and get you set up on that. Thursday, we'll kind of have a review day for you to work on your signature assignment or finish your reviews for the test. And then Friday will be the chapter 9, 10, 11, 12 tests. So 9 through 12 chapter test is going to be Friday. So if you have any questions or need any help, please let me know, and I will see you tomorrow.